topic of today's video will be limit and continuity of a complex valued function, right? And as you know from the study of a real function, what is the concept of limit means we say that for a real function fx, a limit is said to exist if the left hand side limit is equal to the right hand side limit, right? I will write that for a real function fx, right, from a to b. Okay, you say that we say limit x tend to x naught fx equal to capital L. Capital L is a real number, right? If and only if the left hand side limit x tends to x naught minus fx equal to limit x tends to x naught plus fx, and that is equal to a real number capital L, right? It means that when you approach this point x naught on the real axis, either from the left hand side or from the right hand side, right, the value of the function approaches the number capital L, and this is called the limit of a function. Means capital L is said to be the limit of function fx at the point x equal to x naught if the left hand side limit is equal to the right hand side limit, right? For example, if I take a function fx equal to take it x square for x less than 0 and x plus 1 for x greater than equal to 0, right? And you can see that if you draw the graph of this function, that will be something like this. This is your y-axis or fx, fine, and on the negative side means for the x less than 0, the graph is of this form, parabola form, and there will be a white circle because at x equal to 0 the function is not defined by this parabola. The value at x equal to 0 will be given by this straight line. So I have made a circle here, white circle, right? And then x plus 1, that will be a line of this form. Here I will have dark circle, and this value is 1, 0 comma 1, right? And this is a line. This is your parabola x square, and there is a line y equal to x plus 1, and you can see that at x equal to 0, right, the left hand limit is equal to 0 and right hand limit at x equal to 0 is 1. You can see from graph when you approach 0, this is a point x equal to 0. When you approach this x equal to 0 from the left hand side, from this side, right, you are having the value of the function is equal to 0. You can see it from here, right? And if you approach this x is equal to 0 from the right hand side, from this side, then the function has value equal to 1, right? And this indicates that the left hand side limit is different from the right hand side limit, and the function, we cannot say that this function has a limit at x equal to 0 because from both the sides we are approaching the different values. From left hand side 0 and from the right hand side it is 1. So limit does not exist. Limit, for example, the limit does not exist at x equal to 0, and that fact is supported by this graph also, right? Similarly, for a complex valued function, what do we mean by the limit of a complex valued function? Because in this case, this is a real valued function. The existence of a limit depends on the left hand side limit and the right hand side limits. Means you can approach a point. I have taken that point x equal to 0 on the x axis. You can take any point. That you have to approach that point either from the left hand side as well as from the right hand side, both sides, and you should get the same values of fx, right? Then we say that the limit exists. But in case of complex functions, because this is a real function and we have two directions to approach any point, But in complex function, first thing is that we cannot draw the graph of complex function. We need two copies of complex planes, right? So drawing the graph of complex function is difficult. First thing is that, and the second thing is that if you have some point, that point is z is equal to z naught on a complex plane, right? Then you can approach that point from different directions, not only from left side or from right side. You can approach that point z naught on complex plane from any direction or through any curve passing through that point z naught, right? So I will try to define the complex limit of a complex function in a similar manner as I have defined this for a real function, right? For a complex function, or I should say complex valued function of a complex variable, fz, right? We say limit z tends to z naught, fz equal to capital L, if and only if, and you can see the difference, if and only if, this is for left hand limit and right hand limit, if and only if limit z tends to z naught, fz equal to capital L, right? And there is no need to write that z tends to z naught minus or plus, because this is a complex number, and as you know that a complex number can be approached through many directions, not from the only the right and left hand side, right? So this means that z tends to z naught along any curve, right? I will write it here, along any curve passing through z naught, and the limiting value should be same, right? So this is a strict condition as compared to the real function, which is having the condition of approaching the x naught from left and right side. But this time you have to approach this point z naught on z plane along any curve. There are infinite number of curves through the point z naught. I will try to draw that those curves, some of those curves, right? And since I need two copies of complex plane, one is the domain plane z plane and the other is w plane, image plane, I will draw only the domain plane, right? Because z naught is a point on z plane and capital L will be a point belonging to w plane, right? I am drawing only the z plane, okay? So this is your y, this is your x, and this is your z plane, right? And suppose z naught is this point is z naught, okay, z naught, right? And you can see that approaching z naught from left and right is possible. Obviously you can approach this z naught from left hand side, this path, or you can approach this z naught from right hand side, right? Or you can approach this z naught from any oblique direction, means an oblique line passing through z naught. So I'm having three directions, as well as you can take any arbitrary curve like this, any curve like this is also possible, right? A spiral curve is also possible, means going in this way, spiral, and then this, right? So I made 1, 2, 3, 4 choices of this curve. There are infinite number of curves which pass through z naught, and for all those curves the limiting value should be same, capital L. If this condition exists, this one, then we say that the complex valued function fz has limit L as z approaches z naught, right? So this is a strict criteria for the existence of a limit of a complex valued function, right? You can see the difference. It has only two ways, one from left and one from right, and has infinite number of curves, infinite number of directions, you can say that, by which the z may approach z naught, right? Okay. So I will try to take a small example for a complex valued function. Let me take it, for example, limit z tends to 0, z over z bar does not exist, right? I have taken a non-example, right, to understand the concept of this choosing a suitable curve through that z naught, right? right? We have to show that this limit doesn't exist, and for that, since limit this z tends to 0 means that is a complex number, x plus iota y means x comma y tend to 0 comma 0, right? And at this point you convert your function, which is a complex function, into a function of two variables. As I have said earlier, there are complex function can be viewed as a function from R2 to R2. R2 means the xy plane and another xy plane, two copies of xy planes, R2 planes, or you can say that one is z plane with x and y axis, and another is a w plane with u and v axis, right? So xy tending to 0 0, x is approaching 0, y is also approaching 0, z tends to 0 means this, right? And here we have x plus iota y, and this conjugate of z, that will be x minus iota y, right? Now my z naught is 0, you can see from here, and this z naught is 0, or you should place it here, right? So there are different ways to reach this z equal to 0 according to this example, right? First obvious choice is to approach this z equal to 0 from this x axis or along this y axis, right? So along approach z tends z equal to 0 or z equal to 0, right, from along x axis, right? And it means that y equal to 0, right? So I will substitute y equal to 0 here. That will give me, implies limit x tends to 0, x upon x. You can see that if I put y is equal to 0 here, then it will become x upon x, right? And obviously y is eliminated, so I have to write only x tends to 0. There is no need to write y because y has been eliminated, right? And then after cancellation it will give equal to 1, right? So you can see that if you approach this point z equal to 0 from the along the x-axis, along a curve on the along the x-axis, that is y is equal to 0, you are reaching the value 1, right? And let me see what happens if I approach z equal to 0 along y axis, that is x equal to 0, right? So you should substitute x equal to 0 here, and that will give me, implies limit y tends to 0 iota y or minus of iota y, right? And this will be cancelled. I think I will get minus 1. Okay, and see that the one limit along one curve, right, along x-axis, the limiting value is 1, while the along the another y-axis, other curve, the limiting value is minus 1. So these values are not same, which is contradicting this fact that along any curve you choose to that point, the limiting value should be same, right? In this case, the limiting value is different, so limit does not exist, right? Therefore, limit z tends to z naught, z over z bar does not exist, right? Fine. So I will take another example. This is my example number 1, and this is example number 2, right? Limit z tends to 0, z over z bar whole square equal to how much, right? Okay, solution. Limit x comma y tend to 0 comma 0 in the same way, that will be x plus iota y over x minus iota y whole square, right? And now you approach, if you approach this xy tend to 0 0 along x-axis, that is y is equal to 0, you will put y is equal to 0 here, you will be getting x upon x, and there is 1 square, and the value will be 1, right? Then we will approach z is equal to 0 along y-axis, that is x equal to 0, right? In that case, we will get iota y over minus iota y whole square, right? And again, you will get plus 1, right? So choosing these two paths, the first is this x-axis and this y-axis, will give the same value 1 and 1, right? But that will not prove that the limiting value of this function is equal to 1, because you have chosen only two paths. One is along x-axis and y-axis. That is not sufficient. There may exist some path that you approach z equal to 0, right, along that path, and the limiting value of the function is different. There may exist some path, right? So this will not give the result, right? So you have to choose some another path, and see this third one, this line, straight line. You can approach z equal to 0 through this line passing through the origin, right? And there are so many lines which pass through the origin, and the simplest one is y is equal to mx, means a line with slope m and passing through 0, right? So I will choose that path this time. Approach z equal to 0 along the path, there is an oblique line with arbitrary slope m, y is equal to mx, and you can see that if you put x equal to 0, you will get y equal to 0. It indicates that this line is passing through the origin. You have to choose that path which passes through that point, right? Okay, then I will substitute this y is equal to mx here, and everything will be converted into in terms of x. Then my limit will be x tends to 0. Then limit x tends to 0. If you put y equal to mx here, then I think x and x will be cancelled. In the numerator and denominator, you will be getting 1 plus iota m upon 1 minus iota m whole square, right? And you can open this square, and you can see that this is not containing any x term, and you have to put x equal to x to 0. So this value will not be equal to 0. Obviously, this is the value of the limit, right, which is depending on m. M may be anything. You can choose any line through the origin with any slope. M is a slope, and for different values of m, the limiting value is different, and indicates that the limit is not unique, right? Depends on m, and therefore implies limit z tends to 0, z over z bar whole square does not exist, right? So these two examples give an overview that how the limit of a complex value function is determined. It is not determined by choosing only two paths, the left hand side, x equal to 0, y equal to 0. There should be some more general curve, right, which should not depend on the value of m, right? In that case, you will declare that limiting value is this much, right? Let me take another example. Example number 3, right? Limit z tends to 0, real part of z, imaginary part of z upon real part of z, imaginary part of z. Real part of z is x, and imaginary part of z is y, x plus iota y, the value of z. So we have to evaluate this limit, right? Solution, limit x comma y tend to 0 comma 0, right? And then real part of z is actually x, this is y, and this is x plus y, right? Now, first, obviously, you will choose this path, x-axis, that is y is equal to 0. If you substitute y is equal to 0 here, you will get 0. Yes, the limiting value is 0 along one path, y is equal to 0. If you choose this path, x equal to 0, right, then again you will be getting 0, right? Means the value of this function, complex valued function, at z equal to 0, if we approach z equal to 0 from two sides, along two axes, one is x-axis and y-axis, they are giving the same value 0, 0, right? Now let me see the third one, this one. If I approach z is equal to 0 along y is equal to mx, right? Because y is equal to mx is a line to the origin with arbitrary slope m, right? If I put y is equal to mx here, then what happens? Approach z equal to 0 along y is equal to mx. This is an oblique line through the origin with arbitrary slope equal to m. If the answer depends on m, like in my previous example, then I will say that limit doesn't exist. But if it doesn't depend on m, then I will say that the limit has that value, right? And let us see what happens if I substitute y is equal to mx, right? This will give limit x tends to 0, because everything will be converted in x, and that will give me, I think, mx, that will produce mx square, and here I will have x plus mx, right? Then you can take implies equal to, right? Then you will see that, or do you see that on cancellation of x in the numerator on denominator, this will give limit x tends to 0 m, and then x over 1 plus m, right? You can see that we have this x here and m over 1 plus m, right? And the first instinct is that if you put x equal to 0 here, then you will get 0, right? 0 if you put x equal to 0, right? And it appears that the limiting value is not depending on m, it is a constant 0, so the limit of this function is 0, which is obviously wrong, right? This is not a correct step, this is wrong, right? Why? Because putting x equal to 0 here will produce 0 in the numerator, right? But what happens if I put m equal to minus 1 in this, m equal to minus 1, right? Because you can choose any line through the origin, and obviously y is equal to minus x is one of those curves passing through the origin, and if you choose that particular curve, y is equal to minus x, oblique line, oblique with an angle of 135 degree with the x-axis, y is equal to minus x, right? And if you choose that particular curve, m equal to minus 1, in that case you will get 0 by 0 form. In that case you cannot say that the limiting value of this function is equal to 0. So if I choose m not equal to minus 1, right? If I say that if this is equal to 0, if and only if m is not equal to minus 1, right? But what happens if m is equal to minus 1, right? But if m equal to minus 1, this limit actually doesn't exist. Limit x tends to 0, this mx square over x plus mx square, mx upon 1 plus m does not exist, right? So the value of this function is ultimately depending on the choice of m in the denominator, right? So you cannot say that the limiting value of this function is 0. This is wrong, because m equal to minus 1 will produce 0 in the denominator also, and that will produce 0 by 0 form, right? You have to take all the cases, all the curves passing through that point. So you will say that the limit will not exist, right? Therefore, limit z tends to 0, real z, imaginary z upon real part of z plus imaginary part of z does not exist, right? So I have taken actually 3 non-examples, right? Before taking an example which supports the theory, that is to have a limit, right? I have taken 3 non-examples to understand the concept of choosing the curves, right, passing through z equal to z naught. Now I will take a supporting example, means when limit exists, right? Example number 4, and let me limit z tends to 0, and if I take simple example, x, no, not x, z square, this is fine. Limit as z tends to 0, z square, value of this thing equal to how much, right? And yeah, or I should change this. Let me take it 1 plus eta. Fine. Let me extend this z square plus 1 equal to question mark. Fine. Now, solution. Limit, it means that x comma y tends to 1 comma 1, right? And then after writing z equal to x plus eta y and then plugging x equal to 1 and y equal to 1, right? You'll have x plus eta y square plus 1, and then you will open it. It will give you limit x y tend to 0 0, sorry 1 1 1 1, and this will give you x square minus y square plus 2 eta xy plus 1, right? And then plug x equal to 1 and y equal to 1 directly, right? Okay, this will give you 1 square minus 1 square plus 2 eta plus 1, and that will produce 2 eta plus 1, right? So this is the value of the limit, and in this case I have not taken any arbitrary curve through this point. Why? See this question, z equal to z tend to 0 means if you put z equal to 0 directly, or you can see this step when you convert this z problem into xy problem, if you put x y directly, then you will get 0 by 0 form, right? 0 by 0 form, and that is not the case with this question, right? This is not a rational function, there is no fraction, right? It is the simplest polynomial, so there is no need to substitute y equal to 0 or x equal to 0 or y equal to mx, because this time you are having a polynomial, right? You can put these values directly. Obviously it has a limit, right? That's why I am able to substitute the x and y directly here, right, rather than choosing arbitrary curves to the point 1 1, right? So the value of the limit is 2 eta plus 1, and obviously if you substitute directly z equal to 1 plus eta here directly without converting it into x and y, if you substitute z equal to 1 plus eta here, then open this square, you will get the same answer, right? So this is a supporting example, the limit exists, right? So similar to the continuity of a real valued function, we will try to define the continuity of a complex valued function, right? I will rub this first. Okay, fine. Now continuity of a real valued function, first I will recall that for a real function fx, we say fx is continuous at the point x equal to x naught, right? If and only if the limiting value of the function as x approaches x naught is equal to the value of the function at x naught, right? Means the limiting value of the function as x approaches x naught is actually equal to the value of the function if you input that x naught directly into the function, right? And you know that what does it mean? It actually means that the left hand limit or the left hand limit x tends to x naught minus should be equal to x tends to x naught plus fx, and that should be further equal to this fx naught. So this is the condition for the continuity of a real valued function, right? And similar to this one, I will try to define the continuity of a complex function. So for let me give an example of this thing first. Let's take a small example. If you take fx equal to take it x square minus 1 upon x minus 1, here x is not equal to 1, and for x is equal to 1 we have this 2, right? And if you see that, first I will find the limiting value of limit x tends to 1 and x square minus 1 upon x minus 1. What does it mean? X tends to 1 means x is approaching the 1 either from left or right side, means x is not actually equal to 1, it is approximately equal to 1. When you approach x from the left or right side, it means that, right? And in that case, if x is not exactly equal to 1, you have to use this function, not this one. This is for when x is actually equal to 1. This is the approaching, x is approaching to 1, right, but not equal to 1. So you will use this function and then you will try to simplify it. If you put x equal to 1 directly, you will get 0 by 0 form, and in that case you will apply that L'Hospital's rule, right? Or there are many ways to evaluate it. You can apply the formula here directly, x minus 1 over x minus 1 multiplied by x plus 1, and x minus 1 factor will be cancelled out, you will get x plus 1, right? And then substituting 1 here, you will get 2, right? And note this step, you have cancelled x minus 1 in the numerator and denominator, and that is due to the fact that x minus 1 is not equal to 0, because you are cancelling x minus 1 in the numerator and denominator, and that is supporting the fact that x is not actually equal to 1, right? Because if x is actually equal to 1, then x minus 1 equal to 0, and in that case you cannot cancel x minus 1 in the denominator and numerator part, right? So ultimately, after cancellation of x minus 1 factor, we get the limiting value of this function as 2, and this is the limiting value of the function, that is actually equal to 2, the left hand side. And now I will evaluate the value of the function directly at x equal to 1, right? This part, f1, what is that? That is defined equal to 2, and you can see that the limiting value, this one, is actually equal to the value of the function, this one. So we say that this function is continuous at the point x equal to 1, is continuous at the point x equal to 1 due to this reason, right? So similarly, the continuity of a complex valued function, for a complex function, we say limit z tends to z naught, sorry, we say fz is continuous at z equal to z naught if and only if, similar to this condition, limit z tends to z naught fz equal to f of z naught, right? And you already know what do I mean by this, right? It has a deeper meaning, right? As compared, if you compare this with this one, it is considered in the case for the x tends to x naught minus and x naught plus from two sides, left and right sides, but this is actually something different, right? Approaching z naught along any curve, right? So this should be equal to fz naught, and if it happens, then we say that the limit of a complex function exists, and then the function is continuous at z equal to z naught, right? Means for the existence of a limit of a complex function, the first requirement is that the limit of the function at z equal to z naught must exist, right? The second condition is that f of z naught should be defined at that point, right? You can see that f1 is actually defined. If I hide this one, if I remove this condition, right, then this will be automatically removed, and in that case the function will not be continuous at x equal to 1, right? Means for continuity, the function should be precisely defined at that point, right? And by writing this line, I have defined the function at x equal to 1. The function has value 2 at x equal to 1. If you remove this condition, then this example will be a non-example of continuity. Then in that case, it will be a not a continuous function at x equal to 1, right? So this is also an important part. The function should be defined at the point z equal to z naught, right? And if it is defined at z equal to z naught, and fortunately if those two values are equal, then we call it the continuous function at the point z equal to z naught, right? So taking a similar example to this one example, if I take fz equal to, let me take it z cube minus 1 upon z minus 1, and this is for mod of z is not equal to 1, fine, and this will give 3 mod z equal to 1, right, is continuous at z equal to 1, right. This function is a complex valued function, and this function is continuous at z equal to 1. Why it is continuous? Because the value of the limiting function is coming out to be equal to this, the value of the function at z equal to 1. We'll see that. First, since limit z tends to 1, right, z tends to 1, and obviously you have to use this condition because z is not actually equal to 1, right. So this cannot be used because this is for mod of that number equal to 1. You have to use this one, right, not equal to, and that will give me z cube minus 1 upon z minus 1, right. And on plugging z equal to 1 here, you will get 0 by 0 form, right. So do not plug z equal to 1 here. Apply some rule of algebra or LH rule in order to cancel that z minus 1 factor. You can see that this z cube minus 1 can be expanded by using the formula, and that will give me limit z tends to 1, z minus 1 multiplied by z square plus 1 plus z over z minus 1, or you can also apply the LH rule, L'Hospital's rule at this step, right, that's also fine. And then on cancellation of z minus 1, because z is not equal to 1, so we can cancel this factor. I will get z square plus 1 plus z, and then plugging z equal to 1 here, I will get equal to 3, right. And you can see that the value of the function at z equal to 1 has been defined, and that is actually equal to 3, the same value, right. And f of 1 is given 3. So these two values are equal. So the function is continuous at z equal to 1. And moreover, if you choose any curve, means if you convert this z function into xy function, writing z equal to x plus iota y, and then on plugging x equal to 0, means choosing the path x equal to 0 or y equal to 0 or y equal to mx, you will get the same result, 3, right. So this function is a continuous function at z equal to 1. Let me take another example. Example number 1, limit fz equal to z cube minus 1 over z minus 1, and here we have mod z not equal to 1, and here I have mod z equal to 1, and here I write 3. Same question, is not continuous at z equal to iota, right, right. And you can see that z equal to iota is given, and if you modulus this z, then modulus of iota is equal to 1, right. So for z approaching iota, we will use this function, and for z equal to iota, we will use this function, right. Solution. Limit z tends to iota, I will use this function because modulus of this z is not equal to 1. This is not actually equal to iota, this is approaching iota, right. I will use that value, z cube minus 1 over z minus 1, right. And yeah, then putting iota directly, because I can put iota here directly, I am not getting the 0 by 0 form. That will give me iota cube minus 1 over iota minus 1, and that will give me iota cube minus iota minus 1 or iota minus 1, right. So this is the value of limiting value of this function at z equal to iota, and you can see that f at iota, because modulus of iota is equal to 1, so we will use this value, is equal to 3, and obviously these two values are not equal, right, since limiting value of function as z is approaching iota is not equal to the value of the function at eta, therefore implies limit, not limit, continuity, as it is not continuous, fz is not continuous at z equal to eta, right. So we have taken two examples of continuity, and let me take another example, a non-example, example number 3. If fz is defined as fz equal to z square minus 4 and z minus 2, right, at z equal to 2. Check the continuity. Check the continuity of fz at z equal to 2, right, and this is a function fz is equal to this one, right. Now first finding the limiting value of this function at as z approaches 2, right. Solution, limit z tends to 2 fz, and in that case I have to use this value, limit z tends to 2 and this is z square minus 4 upon z minus 2, and you can apply a formula here, because if you plug z equal to 2 here, you will get 0 by 0 form, right. So it indicates that you have to apply a formula or there will be some cancellation of some factor, right. So applying formula here, z minus 2 multiplied by z plus 2, the factor z minus 2 will be cancelled out and you will be left with z plus 2, and on plugging this 2 here you will get 4, right. This is the value of the function, limiting value of the function as z approaches 2 along any direction, right. And again you can verify that the value, limiting value of this function is 4, means the limit exists of this, for this function the limit exists, and that is actually equal to capital 4, that is denoted by capital L by choosing any arbitrary path, right, passing through z equal to 2, right. And but what about this f of 2? This is not defined, right. You cannot use this function for z equal to 2, right, or f2 is not defined precisely. So f2 is equal to question mark, not defined, right. Therefore fz, we cannot say that fz is continuous, not continuous at z equal to 2, right. And in order to make this function continuous at z equal to 2, you have to redefine or define the value of the function at z equal to 2, right. If you define by yourself f2 is equal to 4, right, then this function will become continuous at z equal to 2, right. But in that case you have to define that f2, right. This is called removable discontinuity, because in this question the function is discontinuous at z equal to 2. So to make it continuous, you can redefine it at z equal to 2, and that's why we call it a removable discontinuity, that can be removed by redefining the function at that point, right. So this is it for the limits and continuity of a complex valued function, right. And obviously these are the steps to understand the differentiability of a complex valued function, then differentiability and analyticity of a complex valued function, and that will be part of our next video. For this video, thanks.